we've had a project going on for about 3, almost 4 years now, looking at center pivot irrigation or even some other irrigation systems and looking at their efficiency. And so since I'm kind of an energy jock, I look at the energy part of it. Dr. Tagvian over here, who'll be talking to you later, he looked at the water efficiency side. So I just kind of wanted to show you what we're up to. Somebody might approach you or you might approach us and say, hey, can you test the efficiency of our irrigation system? And so I just kind of show you what's involved with that and how it's done. So let's see. We got a bunch of people involved in this. The folks here at the experiment station, Cameron, and I thought I saw, and Jason. So anyway, so why the interest in this? It should be pretty obvious. The first would be economics. If the system is inefficient from an energy point of view, that's costing money. And it turns out that the energy costs for center pivot irrigation, whether it's fuel, natural gas, or electricity, that can be a significant part of that crop cost, right? So that's kind of where I come at it, is the cost of energy. I do a lot of industrial audits, and it's kind of the same thing, trying to save people some money. Now, that doesn't mean that there isn't some environmental sides on it too. This is one of those cases where the economics and the environmental sustainability work hand in hand. If I can use less energy, then less pollution. But we've also got this groundwater issue out here. Most of these tests have been done here in the western part of the state, out in the Panhandle, the Ogallala Aquifer. We'll talk about that in a little bit. We've also looked at Rush Springs, and then Don and I went actually out to the eastern part of the state and looked at some stuff too. But most of it's out here in the west, okay? And we know that the groundwater recharge rates on some of these aquifers are pretty slow. Depends on where you are. Sometimes they're so slow that you just consider they don't recharge, really, not in your lifetime. And so looked around, and if you're familiar with some of the Lubbock areas, they've really had some dramatic water level drops, and some areas are kind of crash landing, and so we don't want that to happen out here. So we'd like at least a soft landing, okay? So maybe your children could still farm this area if they wanted to. You crash land, no, you're back to precipitation. So water efficiency and effectiveness usually leads to more consistency too. That's kind of from the old quality control studies. Talk about that in a little bit. You've probably seen a map like this. This is the Ogallala going down through Panhandle. You recognize this area down here probably. That's Lubbock. And the darker the colors get, this is the water level change in feet, and I think this is in the last 25 or 50 years. We got more than 150 feet in these areas right here. Won't go into it too much, but there have been some studies come out of Kansas, Jay Butler, who basically was showing that if you could cut back on some of the water usage as little as 20%, you could actually stop some of this decline. Now that's up in Kansas, but it's still the Ogallala, different geography. I remember I was at the governor's conference when I heard that, and I was surprised, because 20% is doable. I thought they were going to say something horrible like 150%, it's hopeless. No, 20%. Now, that doesn't mean it's 20% everywhere, but that was a good sign. So this study kind of is looking at things like that. Water withdrawals in Oklahoma. Yeah, still the darker areas here are more, and that kind of makes sense, okay? And that's millions of gallons per day. So for the different counties. So what makes irrigation efficient or effective? Well, they're two slightly different things. Well, we've got the plant, which we mean the engine or the motor that's powering the pump. So it's got energy efficiency. That's what I'm interested in. Then we've got the pump efficiency itself, whether it's downhole or topside. I'm also interested in that. We've got the water distribution efficiency, which Dr. Tagvian and his team works on. We actually start putting these things together. And then there's things like operations management. You could have the most efficient devices in the world, but if you're not managing it optimally, that could be putting you in a hole. So this This project really looks at the first three, even though we understand that bad operations management could just trump all these things, okay? But that's for a different study. Okay, so what does this involve? Some of you probably know how this is done. We measure the depth of the water before and after pumping. Sometimes we have to let it pump for a while to let it come down to a steady state condition. And we'll have a picture later that I'll talk about. Sometimes it's hard to actually figure out the depth on these. So this depth of water is the total dynamic head. I'm not going to get into a bunch of equations, but depth of lift, or how much lift there is one of the major components to the energy usage. If it's 400 feet down, that's going to take a hell of a lot more energy than if it's 20 feet up. When Don and I were out east, the depth to the river was like 10 feet or something. The river's right there. Okay, that's a lot different than out here where it can be, 300 feet down to the water table. And if it's electrical, we measure amps, voltage draw, power factor. A lot of what Professor Merrick was talking about, we run into. We have seen some pretty sketchy electrical setups. In fact, some we've had to say we can't work on this, and we've pointed out where there's problems. I've seen fuses completely burned out, stuff not grounded, things like that. And we don't tattletale on people, but we just tell the producer, it's like, here's the situation. We can't test this, okay? So anyway, assuming everything's all right and we can do our tests, we look at the kilowatt draw of the motor, or we try to figure out the fuel coming into the internal combustion engine. Okay, we measure the RPM of the pump. This helps us to understand the pump performance, especially if we can get some nameplate data off the pump. If I know the RPM and I know what kind of pump it is, then we can go back and look into some tables and see, is this thing flowing the way it should? Then we measure the water flow rate using this kind of interesting device, a ultrasonic flow meter that clamps on the outside of a pipe. That way we don't have to break the pipe and get in and put an impeller in there. It's kind of neat. It doesn't work 100% of the time. It works about 95% of the time. If the pipe's real rusty or something where it's got a bunch of silt in it, then this thing gets a little goofy. And then we have a pressure gauge on it. And basically with those things, this gives us what we call the water horsepower. And it actually is a horsepower. And so out the outside of the pump, where the pump is pushing water out to the center pivot, that horsepower, we look at the horsepower that's coming into it, and we just divide the two, and that gives us an efficiency. Yeah, some photos. There's the ultrasonic flow meter right there. It's just kind of chained to the pipe. Let's see, there's the pressure gauge. And this, in this case, this is a fuse box. By the way, this is that corner high leg that Professor Merrick was talking about. 2 fuses and a block. At first that kind of confused us. It still does a little bit. I'm going to have to talk to him about that. But anyway, you'll see all sorts of stuff out there. This is the internal combustion engine. A lot of that used out here because we're so deep to the water level that we need big horsepower. And a 200 horsepower electric motor is probably that big around and like that. So it's better to just put a 350 Chevy on there, natural gas. This right here is the gas meter that we use to measure the gas supply coming in basically to the engine. We separate the gas line from the meter, put this in between, let it go. This kind of looks like a Roots supercharger. It's a Roots blower. It's made by Roots, actually. The way it works, kind of interesting. And that way we get the fuel flow coming into the engine, then we calculate the water horsepower coming out, and again we get an efficiency. Okay, there's the ultrasonic flow meter. This is flowing, what, 744.588 gallons per minute. So that's a neat tool. It's kind of expensive. And we've got all sorts of, this is electrical, amp probes, things like that. Now, so one of the questions, this is kind of interesting. This is a rather simple test. The question is, well, how low is the water actually? And so we use this thing called a depth sounder. It's basically, what it looks like is it's kind of like a big fishing spool, and it's got a line that goes down, and it's got a conductivity sensor at the bottom of it. And when it hits water, that creates a little circuit, and this thing starts beeping real loud. And so this is one of our grad students putting it down the pump base. Now this is where we get into some trouble is, and if you ask us if we can kind of do this for you, we're going to have to drive a ways to get out here. And a lot of times we'll come out here and these pumps will not have these access holes. So we're going to try to start asking people ahead of time, can you go out and can you examine? Because some of the real old ones don't have these access holes. And so we'll drive 150 miles, come out, and it's like, sorry, can't do it, and have to turn around and go home. Because that depth is that total dynamic head. That is so crucial to this calculation that if we don't have it, can't do anything. The other thing that's interesting about this is sometimes I'll ask the producer, it's like, how deep do you think your water level is? And there's been a couple of times where people said, about 150 feet, something like that. And before we've even started pumping it down, we're down to 250 feet. It's like, whoa. So that's a disconnect there, right? So just doing this simple little test really tells the producer a lot. Okay, so a few graphs. We've done about 42 of these things now, most of them out here in the west. And this is just kind of showing you the difference in depth. This right here in the middle, where it's about 100 feet, this is mostly Rush Springs aquifer, so a little bit to the southeast. This stuff up here is Ogallala, pretty deep. Some of it getting close to 400 feet. This over here, these little ones were kind of odd. They were in a slap out, I believe, and they were in a next to a little river, so the water level wasn't very deep at all. So we get all sorts of different depths. Now this is the Ogallala groundwater levels. I'm not trying to depress you, it's just kind of the way it is. In general, you can see from about 16 years, it's dropped on average a fair amount. The reason I show this is if groundwater level is such a major component of energy use in irrigation, do you think that over time the energy use is going to increase just because of the drop? Yeah. And so when you design a pumping system, you always design the total dynamic head. So if you install this thing here and it was designed correctly, 5, 10, 15 years later, this thing is no longer designed correctly. The groundwater level has changed dramatically. And so now the efficiency's off. I won't get into the math of all that, but it makes sense, right? Okay, so energy required for irrigation, well, pumping pressure is one. Sometimes we'll see very, very high pumping pressures. We've seen 90 and 100. And I asked the producer, it's like, why is this so high? And he goes, well, if you stick around for a couple of days, you'll see it drop as everybody else around me turns on their center pivots. So that's the problem about us coming out and just taking snapshot views. Sometimes we don't get the whole story of what's going on. And this pumping pressure, of course, related to depth. Distribution losses, that's more Dr. Tagvian. What happens with these pivots? How are the nozzles effective? Are they overwatering? What's going on? Application losses, again, nozzles. Then, of course, we've got to get the span around, and that could be electric, hydraulic. And then there's a few controls and lighting on them. But that's essentially where the energy is, and it is 80, 90% pumping, obviously. This lighting stuff is very minimal. So here's kind of how it works. Once we know the energy coming in and we know the energy going out from water horsepower, then we figure out our efficiencies. And this is basically something called the overall pump efficiency, or OPE. Now we compare the OPE to some accepted standard, and we use the Nebraska Pumping Plant Performance Criteria. I call it NPC. I don't like saying the letter P that much. And it's a standard that's used by quite a few states, and it's not 100%. It doesn't say, yeah, you got to run this. It's a reasonable standard over time that they've determined that, yeah, you know, this thing should be around 67% efficient. So then the difference we measure in the OPE at maybe your plant versus the NPPC, which is we believe is an achievable number, that's the amount of energy you could save. And then we can equate that to dollars. So then we can also look at some other things that are going on and try to figure out, is it the pump? Is it the motor? Is it something else in between? But that's essentially what it is. So we look at a variety of clues. Now, this is just a bunch of numbers, but essentially this is the NPC numbers. So this is the benchmark, and they've got it for electric, diesel, natural gas, propane. I hope nobody here's using propane, that's pretty expensive, or gasoline. And we convert these to percentages, okay? Let's see, so what causes a lot of this? Well, you know, common sense things, worn out, detuned engines, motors, the pumps. Pumps are a major issue. Clogged, compromised pumps. I mean, some of these pumps have been underground for a while. You've got sand, a lot of sand in places. If you've ever had to pull your turbines out, sometimes you'll see the casings have actually eroded away. We've seen that where you can see daylight straight through them. Incorrect pump components for the current situation. When it was installed, maybe it was designed correctly, but now 10 years, 5 years later, water tables dropped. Now it's off the efficiency curve. Bad electrical power wiring or components. You know, we've seen that. Yeah, well, changing water table, that goes with the one above it. So this is not all of them, but I just kind of wanted to show you what this looks like. These are electrical pumping plants here, so E1 through E14. Here's this green line is this NPC standard. So that's the standard we think that you could reasonably achieve. This red line is the average of these, 14? And we've done a lot more than this by now. That's quite a bit of difference. That's what, 49% to like 67%? That's a lot of money. And then down here are some natural gas ones. Of course, we've done a lot more natural gas. The thing to notice about the natural, it looks smaller, but that's because of the way the percentages are actually reported. Look at that, they're only halfway to NPC. That's a lot of fuel that's being used. The natural gas engines tend to be the ones that have the worst efficiency just because they got a lot of moving parts and they wear out. Okay, here's the energy cost analysis for the same things. The gray is the pumping cost in thousands of dollars per year, and the kind of orange here is the potential savings. So this varies depending on what pump you're looking at. Oh, by the way, I just want to back up real quick. Notice that some systems are actually at NPC, and if we looked at all of them that we've looked at, probably about 5% are actually above NPC. So NPC isn't the ultimate you can achieve, it's the reasonable you can achieve. All right, switch gears real quick here. This is looking at how uniform the watering is, the water application is, and use some little numbers here. The main thing is that we'd like to get up around, what is it, 80%, something like that? He just left. And anyway, so we can see that our average tends to be a little bit lower. That's things like clogged nozzles, stuff like that. This is an example. What they do is they put out these little catch cans so many feet apart, and they let the arm swing over it while it's irrigating, and then they look at the catch cans, and if you can just see how inconsistent this is. What do you think these are down here? What do you think's going on down here at these bottom ones? Clogged nozzles, yeah. Or you'll see an end gun that's broken and this number will be way up here. So this is very inconsistent, and so what the producer will often tend to do is to make up for this, they'll crank everything up. So that's why it's important on the water side. Yeah, here we've got a malfunction right here. So the catch can, of course you see this with your eyes, but this is more kind of what you want, more consistency like this. So those are the two studies that are going on. You've got the energy side study, which is what I'm doing. I'm looking at energy efficiency. We've got Dr. Tagvian, you're looking at water application efficiency, and it kind of brings these two together. If you can fix the energy side, if you can fix this side, you're doing about as good as you can do. There's the little catch cans. So that's always fun. We go out there and sit around while this span goes over it. Then they go out and slog around in the mud, picking them up. I think this is about the last slide. Yeah, you discover all sorts of interesting stuff when you pull up these. This is a depth sounder that we were having a lot of trouble with, and it turns out that the casing on this one had broken. It had actually eroded through, and so mud was being pumped into the casing. Couldn't figure out why I couldn't get a continuity on it. Couldn't figure out what the water depth was. I was just pulling up mud for like 30 feet when I pulled the line up. So.